Hello everyone, welcome to month 7 of AOA, and today we'll be examining compression algorithms. So as a brief lesson overview, we'll talk about the definitions and uses of compression, as well as various data compression algorithms, which include lossy and lossless compression. So briefly on the basics of data compression. So compression is the process of making data smaller or compressing it, which you might have seen when you download files off the internet, which are often compressed or in .zip files. So compression algorithms work by basically finding patterns in the data and representing them using smaller values. Lossless compression is compression, which means that you can get back all the data that you put in without any loss of information, whereas lossy compression algorithms are typically more efficient but result in some kind of data loss. So common applications of compression include their use in text files, image files, audio files, and video files, which is especially evident if anybody has watched a YouTube video, which are basically all compressed. So on the differences between lossy and lossless compression. For lossless compression, compressed data is formed in a way such that decompression algorithms can bring back the original file without any loss of information. So some examples of this would include the gzip, pkzip, and png file formats. And this is useful especially for image and video because it means that you can have the full image quality of the original file without taking up so much storage space. This is typically less efficient than lossy compression because there needs to be a way for decompression algorithms to bring back every single piece of data that was in the original file. As for lossy compression, you allow for increased compression because you're okay with losing some data clarity, and this is typically done in file formats such as JPEG, MP3, and MPEG. The first algorithm we'll look at is the Shen compression algorithm, which is commonly just called the Shen compression algorithm. So there are 7 steps listed on the left, but the basic gist is that you order every single letter or number or character in your string based on increasing probability. So what that means is that you'll have the most probable or character that appears the most frequent on the left, and you'll have the least frequent character on the right. Then you'll divide the symbols into 2 groups, and you'll try to maintain consistency such that the group on the left is just as probable in total as the group on the left. So what that means is you might not have the same number of characters in every single group, but you maintain that there's about a 50% chance of picking the left or the right. Then you'll repeat these steps until you've made a tree, such that your tree's end nodes are different characters. Then you'll assign a 0 to the left tree and a 1 to the right tree, and you repeat this until you get a sequence. So that might be tough to visualize in your head, so let's look at a brief example. So for this example, we have a tree here. The different characters in the string are A, B, C, D, and E. The first step is to split the data up as well as you can into 2 groups such that they're kind of even. So A and B are on the left, and C, D, and E are on the right. So A and B occur 21 times, whereas C, D, and E appear a total of 14 times. That's the first division. Second, within each subgroup, you want to split it as evenly as possible, even if that's not always the case. So for A and B, the split would just be A and B. And for C, D, and E, the split is C and then D and E. And then finally, within D and E, the split is once again just D and E. So how does the compression algorithm actually work? Well, if you wanted to represent A, you start from the root and you go left once and then left again. So that would be 0, 0. Whereas if you wanted to go to B, you'd go left and then right. So that's 0, 1. Likewise for C, you'd go right and then left, which is 1, then 0. And onwards for every single character. Finally, talking about the Huffman algorithm. The Huffman algorithm is another common algorithm used for compression of string data. This also takes a binary tree, much like the last one, with no particular order of the symbols. You'll basically repeat the same steps, making a tree until every single character is represented, assigning a 0 and a 1 to the right side, and then you'll traverse the order and assign every single character a unique designating code. So for example, if you look at this, there are a bunch of different characters here, and you'll put all of them in an order, and then you'll make it so that when you split the data apart, everything comes together with a 3 or 4 or however many digits there are code. So how does this actually work? Well, when you send data, instead of sending the full string, you'll just send code of the 001 or 002, which is a lot less data than to represent a character. And you'll also send a dictionary. So this is only efficient for kind of larger pieces of data. Whereas if you're just sending one character, sending together a code combined with a dictionary might actually result in a higher file size.
Alex has covered some algorithms that use binary search trees. Now I will be going over lempo-ziv and run-length encoding, both of which involve pattern recognition, but like Huffman and Shannon also involve the use of a dictionary. How lempo-ziv does is it starts reading through the string of text and is also able to look ahead for pattern recognition. After traversing through the string, it'll check back to see if there are any repeats of a specific character or a group of characters. If there are, it will go back to the last occurrence and record the number of steps needed to go back. It then keeps a pair of values, one of which represents the position and the number of bytes contained in that given group that is repeated. After that, you concatenate the position length pair into the compressed string, and then you can also decompress by reading backwards the compressed string. Now let's look at an example. So here we see that the first byte is just A. Since there aren't any A's before because it's the first byte, it's recorded as 00A. The next byte is also an A. And if you look back, the previous one is also an A. So then the next output that gets recorded is 1, 1. The first one represents that it's been repeated one step before, and the second one represents that the length of the repeated byte is also 1. The third position has a B. Since B has not showed up before, it's recorded as 00B. And same for C, because it hasn't been recorded before, it's 00C. Now we get another B. Here it's recorded as 2, 1 because another B shows up 2 steps before. And in position 6, we have 1, 1 because there's a B at position 5. Now, bytes 7, 8, and 9 represent A, B, and C respectively. A, B, and C show up in 2, 3, and 4. And that means that if you go back 5 steps, you're able to get A, B, C as well. So that's why the first value here is 5, and the second value is 3, because the length of the repeating string is 3. Now, if we were to record this compressed string and we want to decompress to get the original message, we can also do it pretty easily. We first see that there's 00A, which means that we just add an A to the output, then 1, 1. That means that we add a single one step, one position after the original one. So it becomes AA. 00B and 00C, you add B and C. Next, 2, 1. So you go back to positions and you see that it's a B, and you add the B. Same for 1, 1. You go back one position, you find a B, and then you add another B. Finally, 5, 3. You go back 5 positions, you grab the first 3 bytes, and then you concatenate it to the end, and then you have your decompressed file. Next, let's go on to run length encoding. This works a little bit differently, but There are many different types of run length encoding. So the first is if there's just a long run of repeating characters, you represent it with the length of the run and the character represented. So if you have a long string of A's, you could say like 5 and then comma A, which would represent 5 A's together. Pretty simple. This can also work for numbers. For instance, if you're trying to compress binary code and you have a lot of ones and zeros, you can pick the number that's running, the zero, and a number to represent the length of the run. So if you have 7 zeros in a row, you could represent it as 07. Alternatively, for a series of numbers, you could also represent the run once again by two numbers, one counting the length of the run and the other representing a number that is repeating. Once again, run length encoding is generally only efficient for if your file contains a lot of repeating numbers that are next to each other. Let's look at some brief examples. For instance, on the first one at the top, A shows up once, so we represent it as 1A, and then 1D, so on and so forth. Now you see here, we have 8Bs in a row. So then we have 8B and then 2Cs in a row at the end, so we have 2C. So we see that if there aren't many repeating letters close to each other, the compression is often less efficient. So you're counting on the fact that the compressed string that you have has a lot of repeats in order to maximize compression. Then if we have a series of numbers, the same process can be done. If you're selectively choosing 0 as the digit to compress, we see that we have 03 and 01, 05, 02, so on and so forth. And finally, in our last example, we put the repeat count first as well as the pixel value. This is especially useful in compressing images, especially when there are certain numbers that represent the color and the size of the pixel. That's all for this month's lesson. Stay tuned for next month and our final month where we will be going over binary search trees.